The notion of a direct sum of two vector spaces is a concept to split a vector space into two pieces. Such kind of thing is also coming up with the concept of exact sequences. So we will look at exact sequences and understand them in a certain way as a special case or just as another view of looking at direct sums. So what are direct sums? One of the problems with this is that it's introduced in two different ways, and there's talking about external and internal, and to understand that this is more like a formal difference. So if you take two vector spaces, let's say a vector space V and a vector space W, so when I say that I mean over the same field, then there is this vector space defined V plus W. The underlying set is V cross W, and then there is addition and multiplication by scalars is defined component-wise. And then the second way, so this is like what we consider to be the external direct sum. In the second situation, you actually start off with two subspaces A and B of a given vector space V. And then what you do is you look at the external direct sum, A plus B, which is defined, and then you define a mapping V called eta into the vector space. Eta is defined by just taking the tuple A comma B in the external direct sum and mapping it to A plus B. So this is a very natural linear map, and if this map is an isomorphism, then we say that V is the internal direct sum. And unfortunately, often in notation, then we do not really distinguish between external and internal. And why is that the case? What's the reason? Well, let's call the result of the external direct sum of two vector spaces V and W, U. Let's say U is the vector space V plus W. In that case, now define a subspace A to be the set of all V comma 0, where V is in V, and define a subspace B, which is the set of all 0 comma W, where W is in W. So now these are subspaces of the vector space U, and the vector space U, which is an external direct sum of V and W, becomes internal direct sum of A and B. And note that this is almost just a formal difference, right? A is of course a vector space which is isomorphic to V. There is the map which takes a vector V in V and maps it to V comma 0 in the vector space U. In the same way with B. B is isomorphic to W. So in this way, there is no real difference between external and internal. It's just when we talk about internal direct sums, we look at subspaces of a vector space and we say those subspaces add up to the vector space V. The vector space V is kind of split. Every vector can be uniquely written as a sum of two vectors, one in the one part, the other vector in the other part. While when we talk about external direct sums, the beginning is different because we start with two vector spaces that a priori have nothing to do with each other. But in the end, the two concepts will be the same. Next, let's say we have given a sequence of three vector spaces over the same field K. So we have a vector space U, a vector space V, and a vector space W. So you call such a sequence of vector spaces and linear maps between them, so rho and sigma are linear maps, a sequence. So if we have such a sequence of vector spaces and linear maps, then we call this sequence exact at V. So in the middle vector space, if the image of the ingoing linear map, so the image of rho, that's a certain subspace of V, is the same as the kernel of the outgoing linear map sigma. Note that such a equality of vector spaces splits up in two conditions. The image of rho is contained in the kernel of sigma. Well, this is actually equivalent to the fact that the composition of sigma and rho is the zero linear map. Why is that the case? Well, let's assume sigma, let's say you have a vector, right? And sigma composed with rho, that's a homomorphism that is of course defined on U. So if we pick a vector in U, then if we first apply rho and then apply sigma, then this means that this is sigma. So in other words, if I take a vector which is in the image of rho, some rho of U, now we're here, that will be mapped by sigma to 0. So that rho of U, which is in the image of rho, will be in the kernel of sigma. So this explains this direction. The other direction, so if I take something in the image of rho and I know it's in the kernel of sigma, why does this show that the composition is 0? Well, more or less by definition. Pick something in U, then rho of U is in the image of rho. Because it's in the image of rho, it's in the kernel of sigma, so if I apply sigma to it, I will get 0. So you see, this is just moving definitions around. So the actually more interesting condition here is that the kernel of sigma has to be in the image of rho. And just wait a second and see what that means. That means if I have a vector in my middle vector space, which maps to 0 under the linear map sigma, then that vector V is actually rho of U for some U in U. So you will see how this condition comes into action a lot, and actually both of these are repeatedly used in what we will do in a second. Well, here are two important examples. Let's say you have this situation, you have the 0 vector space, so that's the set which contains only of the 0 vector. You have the vector space U, and you have a linear map. Well, there's just one, because the 0 has to map to 0 in U, so we don't even give that linear map a name. And then you have a linear map, a rho, into a vector space V. Then we will say, well, we know what it means to be exact at U. It means that the image of the ingoing linear map, of course that image is just 0, is the kernel of the outgoing one. So being exact at U just means here that the kernel of rho is just the 0 subspace of the vector space U. Well, if the kernel of a linear map is 0, we know that this is actually equivalent to rho being injective. So this formalism of writing a sequence like that, saying it's exact at U, just means that rho is injective. And there's a similar condition if you have a linear map, let's say sigma, from V to W, and then you have a linear map into the 0 vector space. Well, there's only one, namely that one, which maps everything to 0. We have no other choices here, right? So this is exact at W. What does that mean? That means that the kernel of the outgoing linear map, which is of course all of W, is equal to the image of the ingoing one, which is sigma. Well, that means that the image of sigma is the whole codomain vector space, and that is of course equivalent to sigma being surjective. Okay. So this will now just use this idea of being exact at some vector space, and we will look at the following definition. So a situation that comes up a lot, as you will see in the future, is the following. We will say that a sequence which is longer, but it starts with 0, then you have U, V, and W, and then you go back to 0, is exact at all the three possible vector spaces at u, v, and w. Let's call that rho, and let's call that sigma. If you have such a sequence which is exact at u, v, w, then you say you have a short exact sequence. Then we say this is a short exact sequence. Since this word comes up a lot, I will abbreviate it once in a while by SES, short exact sequence. Note what that means. That means rho, it means three things. It means rho is injective, it means sigma is surjective, and it means that the kernel of sigma is the image of rho. So the second part of the definition will say, well, if you have such a short exact sequence, then you will say, so a short exact sequence as above is split if there is a linear map let's call that linear map gamma. And that linear map gamma will actually go from W to V. So such that if I first apply gamma and then I apply sigma, notice that this is a mapping from W back to itself, then this will be the identity map on W. So usually one has in mind the whole picture, so one sees the whole short exact sequence. And here you have your sigma, and then here's the gamma. And our condition, what it means is starting in W, going this way, first along gamma, and then back sigma, you get the identity on W. So here's an important theorem, which is very, very easy to prove. So if you have, if the middle vector space V is a finite dimensional vector space, remember, so we're looking at this short exact sequence of vector spaces. Of course, think about it, if V is finite dimensional, then both its subspace U and also the image W under sigma will be finite dimensional vector spaces. So let's still call that sigma here, that linear map. So if V is finite dimensional, then every short exact sequence with V in the middle, that's what that actually means, is split. So you find that linear map with that condition, and you will see in a second what that has to do with direct sums. So here's the proof of that. Well, it has to do with the fact that W is finite dimensional. So since W is finite dimensional, we can pick a basis Z1 up to Zm. This is a basis for W. And now I can of course choose y1 up to ym in the vector space V such that sigma of yi equals zi. So you have here, just see V and W for the moment. Here you have your sigma. So we've chosen a basis in W, and we call those basis vectors zi. And all what we do is we choose, because sigma is surjective, we can do that. We can choose vectors yi in V, which map by sigma precisely to zi. But now we know we can define a linear map by telling what it does on basis vectors. So we can define gamma from W to V by gamma of zi equals wi. And no, not wi. Gamma of zi is gonna be yi. That's how I actually define the corresponding vectors. So gamma will just go backwards, right? And of course now if I take a zi, the corresponding yi was precisely defined such that it's mapped by sigma to zi. So by the very definition of the yi's, I see that if I first take gamma and then I take sigma, I'm gonna get the identity map on W. Identity linear map. That's the whole proof. Note that actually, if you look at this, all this part here hasn't been used. So what this argument really shows is if you have a surjective linear map from a vector space V, which is finite dimensional, to a vector space W, and if you think even more, the finite dimensionness of V is not really used. We actually only use that W is a finite vector space. So having a linear map from a vector space V onto a finite dimensional vector space W, then there is this splitting map. Usually this is used in the framework of short exact sequences. That's why I kept on stating it here. So here's our main theorem relating now short exact sequences and direct sums. So let's state that as a theorem. So if you have given any short exact sequence of vector spaces, let's say 0, u, v, w, 0, here you have a linear map rho, here you have a linear map sigma. So if this is a short exact sequence, remember that means it's exact in all three places, which I can think of rho being injective, sigma being surjective, kernel of sigma equals to the image of rho. And let's assume V is finite dimensional. Then any splitting gamma, so of sigma, one talks about splitting of sigma or splitting of the exact sequence, gamma, of sigma, well, that's a linear map from W back into V, and I should say for any splitting gamma, we have that the vector space V is equal to, well, note that rho of U is actually on the nose a subspace of V. Note that gamma of W is a subspace of V, and the internal direct sum of those two subspaces is the subspace V. So when I write it like that, of course I mean internal direct sum. If you think about that, I could also say that V is isomorphic to the external direct sum of U and W. And if you are not careful with introducing these isomorphisms, then people just say V is the direct sum of U and W, and you will find that a lot. So let's give the proof of that, and let's maybe here start on this slide with the first. Well, how do we prove that a vector space is the internal direct sum of two of its subspaces? Well, the first thing to prove is, and I may indicate it like that, this still has to be proven, this equality sign, that V is actually equal to rho of U plus gamma of W, where this, without the circle around the plus, is the set of all rho of U plus gamma of W, where U runs through the whole vector space U and W runs through the whole vector space W. Now how do I see that? Well, let's pick a vector V in my vector space V. Then let's just consider the vector W, which is the image under sigma of the vector V. This is a vector in W. Now I can use the splitting to go back. I can look at the vector V minus gamma sigma of V. This is again now a vector in V. Now the funny thing is, if I apply sigma to this vector, so let's do that. So if I calculate sigma of V minus gamma sigma of V, remember sigma is linear, then this becomes sigma of V minus sigma gamma sigma of V. Well, these are all compositions here in the end. So this is actually, remember, first gamma and then sigma is the identity on the vector space W. So this becomes just sigma of V minus sigma of v, which is the 0 vector. But now we're in good shape. I mean, now we know we found the vector which is in the kernel. So v minus gamma sigma of v is a vector in the kernel of sigma. But that's our main assumption, is the exactness of that sequence, right? So if you go and look back here, we know that the kernel of sigma is the image of rho. That was one of the three important conditions here. And so I can write v minus gamma sigma of v as rho of u for some u in u. And you see, if I call now sigma of v w, then we have written v in the form gamma of w plus rho of u, which is precisely something in the sum of those two vector spaces, right? So this is the first condition that you have to kind of like check. The second condition is that the intersection of those two vector spaces will in fact only consist of the 0 vector. Let's do that. So the second part is supposed to show that rho of u intersected with gamma of w consists only of the 0 vector. Well, it's intersection of two vector spaces, so the 0 vector has to be in there. So let's pick a vector v in this space rho of u intersected with gamma of w. And let's see. So what does that mean? Well, it actually means that v is rho of u for some u in u, and v is also gamma of w for some w in w. So there's a u in u and a w in w, and they will give you precisely this. So yeah, let's maybe better start all over again for the second part of the proof. So remember, we have this situation that we have this short exact sequence. And these are the names for the homomorphisms. And if this is a short exact sequence, then what was left was to prove that rho of u, that's a subspace in V, intersected with gamma, which is a splitting of w. So gamma of w is equal to just the 0 vector. So we already started. How do you do that? Well, you pick a vector and you show it's the 0 vector. So if I pick a v in rho of u intersected with gamma of w, I know I can write that vector on one hand as rho of u for some u in u. And I can also write it as gamma of w for some w in w. And now apply sigma. Well, sigma of v will be sigma rho of u, but now this will be the 0 vector by exactness of the exact sequence, right? So this is precisely what exactness means. It means that, I mean, among other things, one of the points is that the image of rho is the kernel of sigma. But on the other hand, sigma of v is now also sigma of gamma of w, and we know that that was the way it was done. Gamma is a splitting, so first gamma and then sigma, that is the identity map on w. So this is equal to w, so this is like by definition of splitting. And so what we say, we see that w is the 0 vector. Well, if w is the 0 vector, then of course also v, which is gamma of w, is gamma of 0, and every linear map maps the 0 vector to the 0 vector, so this is the 0 vector. So this completes the proof. This is a different proof than you may have seen in the book, which uses basis, but I think it's way more conceptual actually to avoid the use of basis in this situation. So I know that lots of you are dying at this point to see an example. So let's look at this short exact sequence. 0, R, R2, R0. So we have the linear map rho and we have the linear map sigma. Let's define rho by mapping the real number x to the pair of real numbers x comma x, and sigma will map the tuple x comma y of real numbers to be x minus y. Then if you look at this, that will become a short exact sequence. Of course, if I first apply rho to some x, I get x comma x. Then I apply sigma, I get x minus x, so this maps to the 0 vector. On the other hand, if you pick a vector in the kernel of sigma, right, so then x minus y is equal to 0, so that means y is equal to x, and so this has the form x comma x. So this is very easy to see that this is a short exact sequence. Now, how do we define a splitting? Well, there are many ways to do that, right? Note that I actually would define the splitting only by telling what gamma of 1 is, but I can of course just write it up here. Let's say gamma of z, define this to be z comma 0. Well, why is that a splitting? If I first take gamma of z and then apply sigma, I will take sigma of z comma 0, which is by definition z minus 0, which is just z. So you see, gamma, first gamma and then sigma gives you back z. So this is the identity on R. Okay, now what is gamma of R? Gamma of R is a certain subspace of R2. That's the set of all z comma 0, where z is real. And what is rho of R? That is the set of all x comma x, where x is real. So these are both subvector spaces of R2, and our theorem tells us that R2 equals gamma of R plus rho of R. And of course I could have just given you those two subspaces and asked you to show that R2 is the, well, internal direct sum of those subspaces, but you see it's just seeing practically the conditions that the intersections of the two are only the 0 vector, and the two vector spaces together, the subspaces, span all of R2, which I also could say it's just plus without the circle around it. Remember that. It's just, this theorem is just giving you another way to see that. I mean, by just writing up the two maps here and picking a splitting. So yes, I mean, it is, these things are just formal. I mean, we're playing with these formal definitions of direct sum. But here, in such an exact sequence, you see how nicely it shows you how in that you can split R2 in many, many ways. There's like a trivial splitting of R2 into subspaces where that rho map would just map to x comma 0, and then sigma would just map x comma y to y, right? And of course something that is in the image of the first map, which has second component 0, then maps to 0. That's kind of a trivial splitting. So of course there are many, many ways to split R2 into its two subspaces and into two subspaces. And I mean, it's you know, you can't really, it seems like a canonical choice, but that's just because of the way we look on R2. Principle, if you think of R2 as the plane, if you have the origin here, any two subspaces would be fine, right? And you could think of the first subspace to be the image of a linear map from R to R2, and the second one, the image from R to R2, not sigma. This is actually gonna be the rho, the gamma. Whoop, that would be gamma of R. Okay.